Good morning, everyone. Welcome to today's Offshore Wind Turbine Radar Interference Mitigation webinar. My name is Patrick Gilman. I'm with U.S. Department of Energy's Wind Energy Technologies Office, and I'll be moderating our session today on the impacts of offshore wind development on high-frequency coastal radars used for wave and current measurements, as well as the search and rescue and other missions. We have a great panel of speakers from federal agencies, universities, and radar technologists today. We're really excited to get into the conversation. Before we get started, just a few quick housekeeping items so you know how to participate in our webinar. Attendees are going to be in mute, on mute by default, but just in case, please make sure that your line is muted. Most attendees are listening in using your computer's speakers by default, but if you want to join over the phone, just pick the telephone option in the audio pane in the webinar panel, and the dial information will be displayed. Please choose only one audio option. You'll have the opportunity to submit questions to our presenters today by typing your questions into the questions pane of the control panel. You can send in those questions at any time during the presentation. We'll collect those and work through those and address them during the Q&A session at the end of our presentation today. Finally, we're recording the session, and we'll be posting the recording as well as the presentation materials to DOE, U.S. Department of Energy's website in the next few weeks, and we'll have a link in the slides, and we'll have that in the chat as well. With that, let's get going. Next slide. So this webinar is part of a series of webinars that the U.S. Department of Energy and its partners in the Wind Turbine Radar Interference Mitigation Working Group, which is a group of federal agencies working on overcoming wind turbine radar interference issues. This is one of a series of webinars in which we're building relationships between the federal agencies and key stakeholders on these issues, sharing perspectives on the impacts of radar interference on different radar missions and offshore wind development, and then identifying R&D needs to address those impacts. Hopefully through these webinars, we can collectively gain a better understanding of these issues, understand the state of the science as far as the impacts and mitigations, and then help develop future priorities for overcoming them in the future. Next slide, please. Next slide. Thanks. So just a couple of notes on the webinar series. We'll be hosting a follow-on conversation to this where you can speak in a little bit more interactive fashion with the panelists should you so desire to talk about the R&D needs, potential collaborations around wind turbine effects on HF radar systems, and please reach out to the organizing team if that would be of interest. We have another webinar coming up next month on air traffic control and air surveillance radars, where we'll have a couple of presenters from the FAA as well as a panel discussion, and then we'll finish off the webinar series in the fall with a virtual roundtable with stakeholders and agencies to talk about R&D priorities moving forward. And again, all of the information regarding this webinar series can be found at the DOE website. At the link on the screen, again, these slides will be posted, and we will make that link available through the chat during the webinar. Next slide, please. So just to get into the agenda really quickly, again, I'm Patrick Gilman. I'm going over the front matter now. Then we'll hand it over to Brian Zelenke from the National Oceanic and Atmospheric Administration to talk about the HF Radar Network. We'll then go to Hugh Roherty from Rutgers University to talk about background on the issue and previous mitigation efforts. CODAR's Chad Whalen and Dale Trockle will follow that up to talk about their mitigation work. Anthony Karincic and Brian Emery will then talk about the effectiveness of mitigations so far and the impacts to observations. Christina Forbes from the Coast Guard will talk about the importance of these systems and accurate information from them to form search and rescue operations. Finally, we'll have Angel McCoy from the Bureau of Ocean Energy Management, who will talk about how these issues will come up in the BOEM planning process. And hopefully we can get through those presentations quickly enough that we'll have plenty of time at the end for Q&A, which I will moderate. Then we'll have a few concluding thoughts at the end of the webinar around 1 p.m. Eastern. Next slide, please. And with that, let's hand it off to Brian Zelenke from NOAA. One more note there, just we'll let all the speakers introduce themselves today so we're not reading long bios. Brian, over to you. Brian, you should be able to speak now.
There we go. The muted by organizer button's off, so hopefully everyone can hear me. Hi, I'm Brian Zelenke, and I'm the lead for the U.S. National HF Radar Network. On this slide, you can kind of see a picture of a model off the east coast of the United States that shows the speed and direction of ocean currents, and this is but one example of the type of data that these HF radar feed into. So I thought I'd talk to you a little bit about the program and orient you. So I'll let most of the speaking on this go to the other presenters today. Next slide, please. So I just want to give you a brief glimpse at the HF radar network, what it does, and then some thoughts in terms of mitigation and how you all may be able to help inform and participate in that. Next slide, please. So on this image, you can see a little green place mark everywhere that there's a high frequency radar ocean surface current mapping station. About 160 of them operating at any given time. And the coverage is pretty much the United States coastline with some gaps that you can see there. Also shown in addition to those place marks is data coverage. I picked a particular hour just to give an illustrative example. You're not supposed to be able to see the detail at this resolution, but just to give you a sense that, for instance, you can see it off the coast of West Coast of the United States, and then also off the East Coast, there's a colored area, and that's showing the measurement field of the HF radars. If you're standing at sea level and you're looking out, the farthest you're going to be able to see is the horizon, and the horizon line's about 5 kilometers away. These radars measure well past the horizon, well past line of sight, routinely to 150 kilometers or more. They can go up to 200 some kilometers offshore, depending on the radio frequency environment. So there's really, given the ubiquity of these systems and their field of measurement, there's really nowhere that's being contemplated that for wind turbines that you could move the turbines and therefore get out of the way of the radars. Everywhere where turbines are contemplated is already measured by HF radars. There's not an avoidance option in terms of mitigation. And the resolution of these things does vary somewhere between 0.2 to 6 kilometers, but it's generally in that higher resolution range nearer to shore and coarser resolution out to sea. Next slide, please. So now a little bit about what HF radar does. Next slide. Won't read it to you, but you can see in the left all the things that we're now doing operationally and also those products that are under development. What I wanted to highlight is this wheel diagram on the right. The HF radar network is part of NOAA's Integrated Ocean Observing System. And you can see in the outer ring of this circle all of the different products, from education to weather forecasting, oil spill response to marine tourism, etc., that the HF radar network has bearing in. And within the next circle, you'll see all the different organizations that have signed on to be partners as part of IUCE, and I do mean that literally signed on, not just in name. And a number of them you can see on the bottom in particular are the regional associations of IUCE, which are our local partners, mainly comprised of academic institutions, but certainly not only, also people from industry and the private sector as well. Matter of fact, you see the one on the bottom, Maricus. the Mid-Atlantic Regional Association for Ocean Observing Systems that my colleague Hugh Rorty will be talking in next. And as you go in, you see all of the different reasons leading to IUs as to why we have the HF radar network. So I just wanted to give folks an appreciation of how many things and how many people's lives these particular data touch on. Next slide, please. So why we're all here, wind turbine interference mitigation. Next slide, please. First, I wanted to clear up something of a bit of a misnomer. We keep calling it HF radar, but actually HF radio is probably a more apt description of the frequency that these devices use to measure ocean surface currents and wave information, etc. So you can see in the left-hand portion of this slide. And if you're wondering what this actually looks like when we say measuring how, without getting into terrible technical detail there, what we get is a backscatter off the ocean surface, and we end up with Doppler spectra that are measured. And you can see the big green arrows pointing to what is called the first order return, and that's where we derive current information, when the red arrows are pointing to regions of second order return, and that's where we get wave information. And turbines that would obscure either of those signal returns cause false information to get put into the either currents or waves, and that's what we're trying to solve. Next slide. So the reason I present this is because on the simplest level, you have a choice. You can either try to solve the problem by dealing with the right-hand side, which is to say, trying to deal with the instruments themselves and the spectra, or it is possible to try to substitute some measurements for what the HF radar systems can do, at least as an addition to the mitigation. So you guys have, when it comes to wind farms, an absolutely wonderful array of possibilities for add-on measurements that you can do within the wind farms, including with current meters and all manner of oceanographic sensors. So I think the opportunity here for mitigation is not just on the right-hand side of this graph, trying to solve problems with the radar spectra and their return, but also asking ourselves how we can be using the wind farms to increase our environmental intelligence and better all of those products you saw in that wheel, which may include making some substitute measurements like equipping the wind farms with current meters and other oceanographic sensors to help ameliorate some of the data that may be lost as we're in this R&D phase here of wind turbine mitigation. Next slide. So with that, I hope I've oriented everyone, and I'm going to leave the rest of the presentations to my colleagues. Next slide. And look forward to taking your questions on this and more at the end of the presentation. Thank you.
All right, thank you, Brian. Next up, we have Hugh Rorty from Rutgers University. Hugh, over to you.
All right, thank you, Patrick. Good morning, everyone. My name is Hugh Rorty from Rutgers University, but I also represent MARC, which Brian touched upon earlier. It's the Mid-Atlantic Ocean Observing System. This here is a picture of our radar installation on Block Island, and in the distance you can see the 2 of the 5 offshore wind turbines that were first installed in Block Island a few years ago. And I'll be talking about how the signals from our radar stations are seeing the turbines and how the history of our network. So next slide. So this is an overview slide of our radar network. It's a collaboration of 6 operators of HF radar to generate surface current maps over the entire Mid-Atlantic, which stretches 1,000 kilometers of coastline from Cape Cod to Cape Hatteras. And we've adopted 3 main frequencies to measure the ocean currents. 5 megahertz or long-range systems to measure out to the shelf break, and 25 megahertz systems that give us high resolution measurements in each of the major ports and estuaries, and then a 13 megahertz network along the coast of New Jersey to assess offshore wind resources. Next slide. So I think in one of the earlier webinars, there was a topic on the discussion of ROTHR, so the relocatable over the horizon radar. So when you talk about HF propagation modes, there's 3 main ones: a line of sight, skywave, and ground wave. And it's the ground wave propagation mode that our technology utilizes to sense the ocean. And it's, as Brian mentioned before, it's that over the horizon capability that gives it the benefit that we derive. So each of the boxes represents the typical range of a different frequency. So typically, if you're standing on the shore, you can see out about 5 kilometers with, let's say, with an optical sensor. But the HF, depending on the frequency that you utilize, can travel anywhere between 30 to 180 kilometers from the shore to give you remotely sensed ocean surface currents. Okay, next slide. Oh, okay. I didn't think I was going to get an animation, but so much the better. So we have here is an animation of surface currents off of Nantucket. We did the simulation back in April, and it just kind of gives you an idea of what the variability of the currents are on an hour-to-hour basis. And this is all derived from the HF radar measurements. Next slide. Okay, so just to give you an idea for scale, that drifter traveled from start to end a total of 70 kilometers over the 3 days, and it was 24 kilometers away from where it was released. So it gives you an idea of the variability of the currents and how far a person or a ship or that's lost at sea, or how far an oil spill could propagate in that time period. So providing the most accurate surface current measurements to NOAA, Coast Guard, and other federal agencies is of the utmost importance in our measurements. Okay, next slide. Okay, in addition to the surface current measurements that the network makes, the network is also capable of measuring nearshore wave height, period, and wind direction measurements. The signal that is required for this is an order of magnitude less than the signal used for the currents. So it's essential that we understand any activities that may interfere with this signal. And we're working with National Weather Service to provide these measurements for them to include in their nearshore wave prediction estimates. Next slide. Okay, and then this figure here gives the audience an overview of the endurance of the measurements. So the x-axis indicates time in years, and then the blue lines indicate radar stations that are operated within the Mid-Atlantic, and then green stations are other HFR stations around the US. We in the Mid-Atlantic were an early adopter of the technology in 1998. And then the NOAA National Network was established in 2004 to gather data from all the other operators. So some of these measurements now are coming up on 20 years of a time series. So a very valuable scientific and a data set that can be utilized in many fields. Next slide. So now I'd like to introduce you to one application of the data, which is providing drift estimates to the Coast Guard for search and rescue. Next slide. So this slide gives you a perspective on the number of search and rescue cases that the Coast Guard will respond to in a given year. Dr. Forbes from US Coast Guard will give statistics nationally, but within the Mid-Atlantic, for instance, there were 2,700 cases for fiscal year 2014. Of note, 90% occur within 3 nautical miles, but there's an even distribution of cases throughout the Mid-Atlantic that extend beyond 3 nautical miles, and it's important that we provide to the Coast Guard the best environmental data so they can perform their search properly and with the most efficiency to hopefully locate someone lost at sea. Next slide. Okay, and so this slide here shows the first evaluation of HF surface current data for search and rescue. Was conducted in 2003. The demonstration shows a 24-hour recording of surface currents in Block Island Sound, along with 3 drifter trajectories. The drifter that the Coast Guard still uses in SAR cases is shown in black. The model that the Coast Guard had been using at the time is shown in red. And the virtual drifter using the HF surface current measurements is shown in blue. So the blue and black track very close to each other, with the HF radar data only showing an 8-kilometer error after 24 hours, while the existing Coast Guard model at the time remained in the sound and had a 24-kilometer error in the same amount of time. So then next slide. Okay, and so this was here just in case the animation didn't play, so we can go to the next slide. Okay, so the HFR surface current product was introduced as a data source to the Coast Guard in May of 2009, and this figure shows the growth in use by the Coast Guard SAR controllers over the past 10 years, where they're accessing the data an average of 100 times per week nationally. Next slide. Okay. So now I'd like to discuss the potential impact to the radar measurements from offshore wind turbines. Next slide. So this figure here shows a typical radial vector map from one of our stations, and we combine the measurements from individual stations to give that map, those animations that I showed earlier of surface currents. This here is our site in Loveladies, New Jersey. Utilizes the 5 megahertz frequency band, and we're getting measurements out to 180 kilometers. So then next slide. So then this figure shows the location of the proposed ocean wind lease area. And with our current processing parameters, we could lose 30% of the data from this station for any given hour. So the aliasing that could be caused in our signal processing due to the turbines and other interference could show this type of impact. Next slide. Okay, so assuming worst case scenario, if we extrapolate out to the other proposed lease areas, then our current measurements on the left would be decimated to what is shown on the right. So it shows a very big impact to the measurements from all the stations in the Mid-Atlantic. Next slide. So then when we combine the radial vectors to generate total vector maps, then our existing product on the left, which captured a nor'easter in November 2018 that caused lots of havoc with an early snowfall in the Mid-Atlantic, could be reduced to what is shown on the right. Next slide. Okay, so I'd like to thank you for your time to introduce you to the Mid-Atlantic HF Radar Network, a tool that the Coast Guard uses, which can heavily be affected by offshore wind in its present state. but I want to let the audience know that there are mitigation methods that are currently available and more that we're looking to develop and test in the coming months. And I'll let the representatives from CODAR, the manufacturer of the radar, and Brian Emery and Anthony Kernsich's colleagues in this field tell you about some of the plans we have in store to evaluate and test these mitigation techniques. Thank you.
Thanks very much, Hugh. We got Dale Trockle and Chad Whelan from CODAR up next.
Hi, thanks. So this is Chad Whelan. I'm the COO at CODAR Ocean Sensors, and I'm going to lead off, do the first few slides, and then Dale will do the remaining part of our presentation. I just want to say a few words about CODAR. We are a small radar manufacturer located in Mountain View, California. We're very niche market. We're very exclusively focused on oceanographic and river style radars for environmental measurements. The technology, so you can see here in the title slide, another view from the site at Block Island. On the left side there is our transmit and receive antenna for 25 megahertz. In the prior slide, you saw the receive antenna for our an older style of our receive antenna for the 5 megahertz system. We manufacture a range of frequencies and configurations for different offshore ranges and resolutions depending on the application. And yeah, this was a fortunate case where we were able to, there were fortunately a couple of our systems operated by Rutgers University, Maracus, and University of Rhode Island, or University of Connecticut, right there at the southeast tip of Block Island. So you can see the turbines there in the distance, 3 of the 5 of them. And then so this created a perfect laboratory for developing some mitigation techniques. So you can, our system was developed in the 70s and early 80s at NOAA in Boulder at the Wave Propagation Laboratory by Don Barrick and his team. Don's now the president of CODAR Ocean Sensors. He commercialized the technology in the mid 80s, and as you saw from Hugh's presentation, over the last 15 years or so, the systems have really proliferated. Both within the U.S., we have about 150 systems in the U.S., and worldwide we've sold over 600 radars worldwide, primarily to mid-ocean agencies. The development techniques, or I'm sorry, the mitigation techniques that we've developed at CODAR are applicable to our radar. We have about anywhere from 85 to 90% of the worldwide market on oceanographic high-frequency radar. But most oceanographic radars, if not all of them, follow the same underlying principles, similar waveforms, FMCW, and very different sort of waveforms and data rates than other radars like Doppler weather, marine navigation, air traffic control, etc. So the techniques we developed with funding from BOEM are applicable to these FMCW radars. And so, our niche is the compact radar you see on the left there, but there are other flavors like phased array systems, which would look more like the fence posts you see there at the bottom of the picture, whose spacing and width along the coast would depend on their frequency of operation. Next slide, please. So the first thing I'd like to do, the second thing I guess I'd like to do is acknowledge some agencies here. BOEM has, under 2 separate contracts, has funded us to both investigate the mechanisms behind the wind turbine interference in our particular brand of radar, which again, the impacts and the manifestation within our data is very different and specialized compared to some of the other microwave radars that you may be more familiar with. So they funded us for a 2-year program to develop the initial sort of, or investigate initially, what the mechanisms are, how we can, predict and track and develop the underlying equations for, predicting where these interference peaks will be. And now we are currently under a second phase where we are now taking some of the mitigation techniques that Dale Trockle discovered and developed under the first program, and actually developing simulation software as well as potentially real-time mitigation software. Well, it'll be real-time software, and we're going to try to evaluate the effectiveness of that mitigation software that will run on the radar systems in the field. And our efforts under the BOEM program have been focused on the 2 radars at the southeast tip of Block Island there, which are operated by Maricus, one of the 11 regions funded by IUCE, and Rutgers University and the other local universities there, University of Connecticut and whatnot. And again, IUCE funds the radar operations there. So Rutgers has been a partner on the first phase of this BOEM project to provide us with the data, which was instrumental in getting this effort going. Next slide, please. And just to give you a little bit of background on the wind turbine interference specifically for HF radar, the first observable impacts on an HF radar were actually in Liverpool Bay in England, where they have a substantial wind farm there, and they had an HF radar operating. And it was one of at least one of the reasons, at least a good portion of the reason, that they had to turn off those systems, because they were no longer they didn't have any mitigation techniques at the time. And so when we saw this, we said, well, wind turbines are coming, so let's see what we can do to try to identify the mechanism of this. And so Calvin Teague of Stanford University and again Don Barrick back in 2012 really looked into this and kind of identified the mechanism for how the turbine echoes impact the HF radar data. And there were some other efforts funded by the DOE there from some folks at Texas, and then again Dr. Trockle really developed under the BOEM program some of these the impact assessments and the mitigation techniques that are now the focus of our development. And then that culminated with a community driven white paper sort of identifying the whole process, which Anthony will be talking about in a while. Next slide, please. And I will at this point hand it over to Dale to complete our presentation.
All right. Well, one of the first things to note is that the way that the wind turbines interfere with the coastal HF radars is a little bit different than how they impact other radars. And with other radar systems, often what happens is that each of the different segments of the blades reflect back the radar signal with a different Doppler shift. And this in turn gives you a region in Doppler frequency with wind turbine interference. But with the coastal HF radars, the amount of energy that's reflected back is below the noise floor and wouldn't really interfere with anything we're doing with our data processing. And a different mechanism is actually what causes the impact. And that's the fact that the radar cross-section of the turbine as a whole is much larger, and that's going to reflect a signal back above the noise floor. And the radar cross-section is also different depending on the position of the fan blades. And so as they rotate through 0 to 120 degrees because of the 3 blades, you get a periodic radar cross-section, which causes an amplitude modulated signal back at the radar. And this amplitude modulated signal, basically, if you break it down into its harmonic components, you find that each one of the harmonic components causes an interference peak in the Doppler spectrum. And just to show you what the radar cross-section looks like, depending on the position of the blades, I have a plot there of in the middle with the blade rotation in degrees, and then on the vertical axis is the radar cross-section. And the different colors represent different nacelle angles of the wind turbine. So 0 degrees would be looking directly into the fan blades, and 90 degrees would be looking at the side of the fan. And so what happens is you get that amplitude modulated signal and those harmonic components causing the interference. And we're going to go look what that looks like in our Doppler spectra. Next slide, please. So Brian Zelinski already showed us one of these Doppler spectra plots from before, but just to review, in the white ellipses there, we have the first order region, which contains the sea echo, which is where we get all our measurements of the sea surface currents. And then the other regions to the left of those are the second order regions where we get our wind and wave measurements. And then you can see the little blobs at the bottom, which are what those harmonic peaks look like in the Doppler spectra of the radar when they come through. And since we know it's those harmonic peaks, we can track those through the through our processing algorithms to find out exactly where those are going to be located. And their location is given by that equation up there on the left, and you can see that it's the rotation rate determines where they're located in Doppler frequency, and then the range is also changes depending on the Doppler the rotation rate. As it aliases around, it pushes it out in range or back in range depending on whether it's a positive or negative harmonic. The key takeaway from that is that just because a turbine is located in the first range cell or the fifth range cell doesn't mean all the interference is going to be located in the same location. It can actually be pushed out further in range or back in range, which further complicates the problem. Next slide, please. And so here I'm just showing a couple ways in which this wind turbine interference actually interferes with our radar's measurements. And the first way is, if you remember from the previous slide, where we have that sea echo region, which we call the Bragg region. When the wind turbine interference is mixed with the sea echo, it's really hard to tell the difference, and we end up processing that interference as if it was sea echo, and it gives us erroneous current vectors. But that's not the only way in which it can impact the current measurements. And so here on the second way is it actually changes our ability to identify the first order region, which is the part containing the sea echo. And for reference, I have two plots to try to display that. And what these plots are, it's basically if you were to take a slice out of those Doppler spectra that you saw in the previous plot at a given range cell. So this is at range cell 3 and range cell 1. Then you would get these, or on the bottom axis, we get the Doppler bin, and then the vertical axis is the power. And the vertical blue lines are there for reference, showing where we've placed our first order line. So that's this region between those is what we think is, or the radar thinks is from the current vectors or the sea echo. And then when we have interference, part of the way we determine where those lines go is by calculating the noise floor from the edges of the spectra. And if we have interference from the wind turbine at the edge of the spectra, we overcalculate or overestimate the noise floor. And so it shrinks our region that contains the sea echo. So you can see on the top plot there on the left side, the blue lines are pretty close together, and there's a clear signal that's above the noise floor to the left of that blue line that should be processed as current vectors or as sea echo, and is not because of the interference on the side. But we can also get the opposite problem where we expand the region that we think is sea echo by having the wind turbine interference near the sea echo. So in the bottom plot there, you can see there's a big spike near the sea echo, which has shifted our blue line to the left again, and it overestimated the region containing the sea echo. And this causes us to process a lot of data as if it were sea echo that's actually not sea echo at all, and causes other problems. Next slide, please. So with that in mind and how those impacts are, what the impacts are, we've gone through and with the preliminary funding from BOEM, we were able to characterize and look at some mitigation methods. And one of the easiest things is simply to tune the radar differently. And with the most effective method being to change the sweep rate. So these two plots on the left here, on the bottom axis is the Doppler frequency, and the vertical axis we've got our rotation rate, and the gray bars going up and down, those are the Doppler frequencies that would contain sea echo. So that's the important part of the Doppler frequency that we're interested in and want to be able to measure. And this is for a 5 megahertz system in this case. And the blue, all the lines represent the location of those different harmonic peaks from the radar cross-section of the wind turbine that we talked about. So that's where the location in Doppler space of where the interference will be for the first 4 positive and negative harmonics. And the blue line is there for reference to show the position of the 4th harmonic peak. So you can see what happens as it aliases around. So the top plot there is the typical sweep rate of 1 hertz. And as that 4th harmonic goes, as you increase the rotation rate, it moves that towards the to the right there, and then it aliases around and comes back in on the left side and keeps going. And this causes that 4th harmonic peak, if you look at it, it crosses the region in Doppler spectra containing the sea echo 5 times, which means there's 5 different regions or intervals of rotation rates that it puts interference just for that one interference peak alone. Now on the bottom plot, we show what happens if we change the sweep rate to 5 hertz, and then basically that unwraps the aliasing and causes it so we don't have any more aliasing happening, which also effectively reduces the number of crossings through the sea echo that we have in Doppler frequency, which is really important in order to eliminate that problem. And in particular at Block Island, where the turbines are rotating between 10 to 12, well, usually the most of the time they're between 10 to 12 RPM, you can see that most of the time in that case, we're not going to have the problem with the wind turbine interference in the sea echo itself, which is a good thing to be able to eliminate. All right, move on to the next slide. But since we can't always guarantee it won't be in the sea echo, we have to also develop other mitigation techniques. And so we can go back and exploit that equation we had before, where if we know the rotation rates and the nacelle angles, we are able to tell exactly where in Doppler space, where those interference peaks are going to show up. And furthermore, we're going to know their relative amplitudes. And knowing their relative amplitudes is important because that means if we know 1 or 2 of them, we should be able to get the amplitudes of the rest. So ideally, we would get a direct feed from the wind turbines themselves giving us that information, but often that's not a feasible case. So what we do instead is we can go back and identify peaks that we think are clearly from wind turbines. So we look for those interference peaks like you see on the left plot up there. And we use those to estimate the rotation rate and nacelle angle of the turbine. And once we have that, we can go back and find all the range Doppler bins that contain wind turbine interference and how strong that signal would be. And then either flag it so it's not processed as current vectors or remove it. All right, next slide. And just real quick to go over kind of some of where we're at in the project so far. As Chad said, we've been working on simulations. We can do small wind farms like Block Islands already, and we've been currently, with our current funding, we're expanding that to encompass large wind farms. But there's still a great need for calibration and validation that's beyond the scope of that project. And in the mitigation, we've developed our basic method, and we're currently developing that into a real-time solution But again, just like the simulation, it's going to require further testing and calibration beyond what we currently have funding for or working on. So next slide. And then just to recap, the key takeaways from this are the fact that the wind turbine interference for coastal HF radars is much different than what you see on other radar systems. And we've done a great job at identifying some useful mitigation techniques that need further calibration and testing. And BOEM has funded a lot of this effort so far. But when we go back to that white paper that Chad talked about, all of the works we've done so far have funding for right now. It represents about 25% of the total effort identified by the community. And I'm going to turn the time over now to Brian and to Anthony to tell us more about that.
Great, thanks Chad and Dale. Anthony Karancic and Brian Emery, over to you.
Thank you. Thanks very much. This is Anthony Karancic. I'm a scientist at the Woods Hole Oceanographic Institution, and I'm going to be talking in this section with my colleague Brian Emery, who works at the University of California, Santa Barbara. And our goal is to tell you a bit more about the community white paper that Dale and Hugh had referred to, and our near-term and future efforts that it proposes. Next slide, please. So last spring, the HF radar community was tasked by NOAA-IUS to meet and self-organize and kind of convene ourselves to assess the potential impact of wind turbine interference, or WTI, on HF radar systems. This led to a series of webinars and Zoom calls, which are very regular for us now, I guess. But it and the result of these initial calls was a small kind of volunteer working group was formed to produce a report that would assist IUS in understanding the scope of the problem and the potential mitigation methods and things to watch out for as we march forward to potential wind farms in the US. The report was delivered to IUS in last June of 2019, and we're going to present some aspects of the report here. But I'd just like to point out that the full document is available online using the DOI number that the link is shown at the bottom of the slide here. And I think it's on the next slide if folks want to grab a screenshot of it or look at it. If you search for that, you can find the full PDF that was submitted to IUS last summer. Okay, next slide, please. So the working group's assessment had two key findings. The first was to support the US's operational and scientific needs, HF radars must be able to collect high quality measurements of the ocean surface in and around areas with significant numbers of wind turbines. Much larger numbers than the 5 turbines at Block Island that Dale had been just talking about. The second key finding was that immediate action was needed to ensure that the mitigation efforts themselves would keep pace with the planned build out of turbines, such that there wasn't a large areas of no observations, as Hugh suggested might be happen for a worst case scenario earlier in this webinar. So I want to be clear here that not only was the group thinking about HF radar operations for folks like the Coast Guard that you'll hear from next, but also the group recognized that HF radar based observational data sets could be quite important to the future operations of the wind farm themselves. In addition to providing operational information for currents for construction activities, but also potential surface waves, as you've heard, and potential development or research projects that are under development for winds and other advanced second order uses of the data might also be useful for the wind energy community. So next slide. Thank you. So this is not just true around Block Island or the East Coast, more in particular, but nationally. As Brian Zelenke showed earlier in his hour, HF radar is a national data product supported by NOAA-IUS. High frequency radar is unique for 2 reasons. The first is because of the combined spatial and temporal resolution that it provides for sensing a coastal ocean. HF radar systems are land-based, they're all weather, they're always on, and they provide temporal resolution of surface currents or other products at the same temporal resolution that a buoy system might, but at many different data points within the coastal zone. And so they also have similar or higher spatial resolutions to potential satellite products that simply can't sample enough times during a day to provide the time series that you would need to really understand the currents and/or waves or winds or other products within the coastal zone. And so they have a unique niche in terms of their measurement abilities, and they're able to deliver that in a real-time manner. So partly because of this, I'm sorry, so it's also unique. The second reason is that they, as a national coverage, it comes from a collection of operators that are coordinated by NOAA-IUS, as Brian Zelenke introduced. These observations are supported by IUS, but they're also funded and supported by the National Science Foundation, individual states or universities that provide both technical support or equipment towards the operational ability of the national system. And so this makes the coastal zone sampling happen in this leveraged environment. And partially because of this, the HF radar community is a broad collection of system operators that are funded both through IUS and other basic science research, hardware manufacturers like Kodar, who are also operators, as well as researchers like myself and Brian Emery, who both operate systems, use the data for basic science research, and develop new products. And so the three areas of coverage that are shown with boxes on this slide are areas with significant HF radar coverage, but they're also areas that are have near-term developments that are planned by the wind energy industry. The next slide, please. So in each of these areas, there are potential significant plans for wind farms, and we're likely to see the types of WTI effects that Dale was describing earlier on HF radar operations. So again, this is not just a Rhode Island or a Massachusetts issue, but it's an East Coast or an East Coast issue, but it's a national issue, depending on how the radar systems, the wind energy systems build out over time. Next slide. So I just wanted to review the interference problem again that Dale was talking about. Dale did a great job describing the wind turbine interference for long-range systems at Block Island. This slide is both a reminder of those impacts on the systems. I have the same figure in the upper right corner that he showed that have been the focus of the BOEM-funded studies, but also to call out that mid-range systems are more likely to be adversely affected by WTI. The images on the bottom of the screen show backscatter from two systems, one that has in view of Block Island, and appears to have interference from something that might be related to WTI or wind turbine interference, but we're not quite sure because we haven't been able to do the work to realize if this is the case or not. And so more work is needed to ensure that these systems, along with the long-range systems that have been the focus of the BOEM-funded efforts, and again, these mid-range systems are more critical in higher traffic marine areas, can be properly mitigated as well. So I'll go to the next slide. And then I'll hand it over to Brian Emery, who's going to talk about the community working group's proposed plan for mitigation activities.
Thank you, Anthony, and good morning or good afternoon as applicable. So as Anthony mentioned, the working group report, I wanted to also say that the working group report really kind of does reflect a community effort. There was a call put out to the entire HF radar community. It's a fairly tight-knit community. We have fairly regular meetings, and volunteers wrote the report. There was the opportunity for comments, and so I just thought I would mention that. A major product of the report was basically a timeline. And the timeline is, given the proposed build out of offshore wind development, what do we need to do? What activities need to happen in order to match that pace so that we can keep the radars operating, keep delivering high quality surface current products? So at the near term, so we divided the timeline up into basically three kind of near and mid and long term. what Dale talked about largely falls under near term. This has sort of been ongoing, and it's been funded mostly by BOEM, and they're developing some nice products. And next slide, please. And what they really need at this point is a lot of in situ data. We need to do a lot of validation and calibrate. So Dale has been developing a simulation tool and models, and we need some in situ data to validate that model and calibrate his simulations. And so a large part of the recommendation of this community white paper was to collect in situ observations, such as the drifter being shown there. And we're talking, large numbers of drifters being released, other sorts of in situ sensors. And I also want to mention that while what Hugh showed did a great job of illustrating the worst case scenario, and that really put up the alarm to people, and I think motivated the community report. But as Dale said, the interference sort of shows up in ways that are not really obvious if you're just looking at a current map. So you could potentially have pretty large error in the current map, be looking at it and not really know that. And that is really important if you're trying to use it to do some science, or you're trying to use it to do some sort of operational effort like search and rescue. An error as small as 1 knot or 2 knots, nautical miles per hour over 24 hours, that's a 24-mile difference. And so, we really want to have a high-quality data set so that we can assess, how well these mitigation methods are working. And so, a midterm outcome that we're going for here is to have sort of a coincident in space and time data set of radars with wind turbine interference in them, and then also instruments in the water, so drifters or other types of current measurements, and ideally rotation rates and nacelle angles from the wind turbines themselves. Next slide, please. And so then in the long term, I should also mention that these midterm and long-term, some aspects of the long-term project we found on Friday are going to be funded by the NOAA Ocean Technology Transfer Project. And if you're not familiar, that's a project within NOAA that takes these sort of research technologies or proof of concept technologies and transitions them to a product. And so like in the report, we use the technical readiness level classifications. And so that is, if you're familiar, it's to take these ideas and move them to a TRL of 9, which is an operational tool that ideally people could buy. And so the NOAA OTT is going to fund some aspects of this and basically get a product developed. It's jointly with CODAR, with Dale and Chad, and it'll be a product available for the CSONs. And so, as Chad mentioned, the CSONs are most of the radars. I think all of the Merrick's radars, for example. Anthony operates a few radars that are not CSONs, and there are a few others. So, in terms of the midterm, the NOAA OTT definitely funds that. Let's see, so next slide, please. So to summarize the report, the community sees WTI as a solvable problem. I think Dale has made some really important steps towards solving this, and that in order to really assess the accuracy of the final measurements, the oceanographic measurements, and assess the methods, the WTI mitigation methods, we need instruments in the water. So that's sort of a primary finding, I think, of the report. So next slide, please. And so to summarize kind of the status of where we are with these mitigations. As I mentioned, the short term has been sort of funded by BOEM, and CODAR has been working on that. We found out on Friday that OTT will fund most all of the midterm kind of objectives that were outlined, and that will result in a product for the CSON radars. And when it comes to the long-term objectives, those included not just the CSONs, but other types of radars, and also some of what are sometimes referred to as advanced products. So things like the waves, and that includes like significant wave height and sea state. Wind direction is something that is commonly used, and other sort of methods that are in development. And so I will end it there, and thank you all for listening.
Thank you so much, Brian and Anthony. It's a refreshing thing to see a pretty well fleshed out roadmap for wind turbine radar interference mitigation for one of these classes of systems. That is certainly not the case for all of the kinds of systems that we're dealing with. So great work on that, and look forward to future collaboration. Next up, we have Christina Forbes from the U.S. Coast Guard. Dr. Forbes, over to you.
Good morning. I'm going to talk about the importance of reliable and accurate environmental data in the U.S. Coast Guard Search and Rescue Optimal Planning System, or SAROP. Next, please. The U.S. Coast Guard is responsible for more than 21 million square miles of nautical miles of ocean, and since 1964 until the end of last year, there have been more than 2 million cases and more than 240,000 lives saved. That means an average of more than 4,300 lives saved per year, or an average of 12 lives a day. Next, please. Maritime search and rescue involves estimating a search area by quantifying a number of unknowns. For example, the last known position and time of distress, the person or object, types and size, and most importantly, the environmental conditions, the winds, the waves, and the currents affecting that object. Then compute the evolution of the search area with time, and rapidly deploy the search and rescue units to the search area. The search and rescue model simulations are used to predict the location and search areas, and commonly trajectory models are used, employing a random walk Markovian methods to account for uncertainties. Next, please. The U.S. Coast Guard uses the Search and Rescue Optimal Planning System, or SAROP, for drift modeling and search planning of persons lost at sea. It became operational in 2007. And SAROP is a fast, comprehensive framework which minimizes the data entry, thus reducing the potential for user input error, accesses near real-time environmental data, uses a Monte Carlo method to simulate the drift of thousands of particles for each scenario, and computes probabilistic search areas. And you can see them here, all the blue and red and green squares, and creates action plans that maximize the probability of success. And you can see the black lines for the search path. Next, please. SAROPs consist of 4 integrated components, a graphical user interface, like you see here, and it's deployed in a series of extensions of S3 ArcGIS software, an environmental data server that provides oceanic and atmospheric data on appropriate spatial and temporary fields to cover the area and time period of interest, a simulator that takes information on the approximate location and time of distress incident to form a scenario like the one shown here. And the Monte Carlo technique is employed to generate thousands of simulated particles to account for uncertainties in the forcing field, the winds and currents, the leeway, drift properties, the initial position of the object, and then creates an ensemble. And the ensemble yields an estimate of the time evolving probability density function of the location of the search object. And you can see the purple sort of cloud there. And each envelope defines the search area. So this is the probability map distribution. And the search planner provides information on where the search effort should be expanded by combining that particle distribution with the availability of search units, or SRUs, producing operationally feasible search plans that maximize the increase in probability of detecting the object. Next, please. So the Environmental Data Server, or EDS, has several oceanic and atmospheric products. The U.S. Coast Guard uses 50 surface current products. This is the usage from the past year. There are about 10 to 15 that are used the most. The ones with the green box use FH radar in one way or another, and I will explain that later. And the ones in the yellow boxes are the HF, the high frequency radar data products used. As you can see, the top 9 usage, 3 of those are products that depend on FH radar. So there are 33% of those. So next, please. So this is the wind product usage. The U.S. Coast Guard uses 33 wind products, and then SD CONUS is the most used. Next, please. And as mentioned before, the high-frequency radar utilizes high-frequency radio waves to measure surface current velocities in real time, and the top 1 to 2 meters of the water column. This is very important for us because SAROPS uses surface current velocity parameters for the drift modeling, are all tailored to that top 1 meter. So this is a very good consistent surface current measurements with SAROPS. And they produce also high resolution surface current fields that can resolve mesoscale features. And the real-time surface currents can be used for model validation. And the HF radar data and the IOOS, or Integrated Ocean Observing System, short-term prediction models are available in SAROPS via the Environmental Data Server. Next, please. So the areas where the U.S. Coast Guard can access or download the high-frequency radar products from the EDS are the East Coast, the Mid-Atlantic, the Gulf Coast, Puerto Rico, West Coast, and Hawaii. Next, please. And there, the Environmental Data Server models that we use in SAROPS and use the HF radar data are the Doppio from the Rutgers University, which uses the Regional Ocean Modeling System, or ROM, for the Mid-Atlantic Bight and the Gulf of Maine, and uses a 4D VAR data simulation method to include the surface currents from high-frequency radar total vectors, among other variables. And the short-term predictive system, or STPS, is a forecasting model that uses statistical information for surface current prediction. It uses CODAR data to produce the surface current forecast fields, and it's also implemented, the one the Coast Guard uses is the one implemented in the Mid-Atlantic Bight and in the West Coast Pacific area. Every hour it creates 24-hour forecast of the current field evolution that is consistent with the most recent data and the statistics of the observed current variability. Next, please. There have been a couple of scientific studies that I like to mention because their results might have implications for the U.S. Coast Guard search and rescue. This study from Boston studied the influence of the large wind farms on the wind fields and the upper ocean response. On the left panel, you can see the extent of the wind farm and the wind stress deficit downwind footprint, the gray area. And This generates upwelling, and you can see it on the right side panel as upwelling and downwelling as the ocean responds. So, so you can see the influence of the wind stress in the upper ocean mixed layer depth. So this upwelling and downwelling modify the surface velocity in the upper layers, and thus also the drift modeling probabilities. So also the upwelling process causes divergence, or the displacement of the surface water, bringing deep cold water to the surface. And SARUP has a component that estimates survival times due to the sea surface temperature. So by changing the surface temperature, it changes the survival time. This might have serious implications on our search planning. Next, please. There is another scientific study on the wake effects and how from wind farms in Denmark using airborne synthetic aperture radars. And you can see the impact of the wind farm. The boundaries are depicted by the red lines, and you can see the downwind velocity deficit. It's the vertical axis, and it's 10%. At up to 3 kilometers away from the wind farm, downwind, and up to 4 or 5%, 10 kilometers downstream from the wind farm. So this finding, together with the previous one, shows that the wind shadowing over the 10 kilometers downwind can also impact the surface circulation far away from the wind farm. Next, please. The 2018 impact assessment and mitigation report shows also that the wind turbine interference impacts the ocean current measurements by affecting the sea echo, and it can cause errors in the velocity measurements up to 48 centimeters per second, which is a lot. So we need accurate high-frequency radar observations for input to the numerical models that drive SARUP. So it's therefore crucial that we understand the possible impact of these wind farms on the radar network and develop techniques to mitigate the impact of the turbine interference. And we need to characterize that interference, quantify the impact, and investigate mitigation techniques, which is what the previous panelists have been presenting. Next, please. So the availability and access to high quality and reliable global and regional wind and surface currents data derived from observational networks like the high frequency radar and from the latest state-of-the-art forecast modeling systems like Doppio and STPS is essential for accurate prediction of the drift of persons or objects in the marine environment, and for targeted search and rescue operation and planning, and to narrow the search areas. If we don't have the correct surface current velocities, then we cannot find the persons lost at sea, and then we have to expand the search areas and expand the time as well, which can cost lives. So the coupled numerical ocean and atmospheric models need to be accurate and depict changes in winds and currents due to the wind farm structures. We also need the HF radar observation. I mean, we need observational networks in and around the wind farms to determine the surface currents and the winds far away from the wind farm as well, and downwind. And we also need the HF radar observations to be accurate so that the numerical ocean models that assimilate them, like the Doppio model, or produce statistical forecasts like the STPS, produce accurate currents to use in SARUP via the environmental data server. Thank you.
Thank you so much. Brian, if we could advance to the next slide. And last up in our presenting lineup today, we have Angel McCoy from Bureau of Ocean Energy Management and their Renewable Energy Program Office. Angel, to you.
Thank you, Patrick. Most of you are probably familiar with BOEM and our mission to manage development of the outer continental shelf energy and mineral resources in an environmentally and economically responsible way. Again, my name is Angel McCoy. I'm a meteorologist in the Engineering and Technical Review branch, where I support the technical review of ocean-based renewable energy facilities. And this includes high-level wind resource assessment for wind energy area identification, meteorological conditions for design and impacts to a facility in the environment, and lighting and marking specifications for facilities. Today, I'm going to give a high-level overview of wind turbine information availability, how the HF radar community can engage with our agency, and the results of a recent study funded by BOEM entitled Radar Interference Analysis for Renewable Energy Facilities on the Atlantic Outer Continental Shelf. Next slide, please. So here we have a timeline of our leasing to operations process. And, today we're not very concerned with much of what's going on the left-hand side of this screen, but I'm going to bring your attention specifically to where I have these two red circles on the lower right-hand side of your screen, where a developer would submit a construction and operations plan, and then where a developer would submit a facilities design report and a facilities installation or fabrication and installation report. You see is that these two steps in our process, in the leasing to operations process, that we get the information regarding wind turbine types and wind turbine placements. As you all have pointed out, as all of the presenters have pointed out, the biggest concerns are, where will the turbines go? How big will they be? What other specifications take place? And so this is just to show you approximately where in our process we start to have this information available to us. At the COP phase, the construction and operations plan phase, is where we get an idea of the turbine sizes, the turbine types, their placement and possible spacing. But that information is not definite or finalized until we get to the submission of the fabrication and installation report and the facilities design report. In between that period, you'll see that upon receipt of the construction and operations plan, BOEM will go through a review to see if that plan is first determined to be complete and sufficient. If it is sufficient, if the information contained there is sufficient, BOEM would then conduct an environmental and technical review process. Perhaps you all are familiar with the term NEPA, the National Environmental Policy Act, where BOEM would then draft an environmental impact statement and go through that whole review process there. And upon the completion of the environmental review and the technical review, BOEM would then approve the COP. It is not until the COP is approved that a developer could then submit the facility design report or the fabrication and installation report. And after a non-objection to those documents, a developer could then proceed with installation. So some of you may look at this and say, well, when does the HF radar community get a chance to engage, to influence the process, to get information? There are a number of steps along the way where you all can proactively contribute to the process. And I'll go into those now. Next slide, please. So to be proactive as a community of radar stakeholders, we have the offshore wind permitting subgroup. This group is made up of federal partners. It is led by our renewable energy program. In this group, you have opportunities for early communication of projects and their paths forward. And the group is made up of a number of federal agencies, all that have some interest or some responsibility, some regulatory authority in the offshore environment. Here's also where the one federal decision timelines are established. Now, unless you all are more intimately involved with NEPA, you may not be that familiar with one federal decision. And so I'm going to explain that briefly in the next slides. So next, please. So one federal decision was established by Executive Order 13807, and it sets a government-wide goal of no more than 2 years from notice of intent for all federal authorizations. I will show you another timeline to help you understand where the notice of intent comes in. But basically, after BOEM receives a construction and operations plan and determines that it is complete and sufficient, like I explained in the slide, the timeline slide, once we receive that, we can then issue a notice of intent to proceed with the environmental review. The one federal decision ensures that federal environmental review and permitting processes for infrastructure projects is coordinated, that is predictable, that it's transparent, and it requires a single schedule. So in the past, the other federal agencies would all work on their own timelines to reach decisions on projects that everyone would have a hand in. So to do away with that kind of extensive process, often drawn out process, one federal decision hopes to, streamline, don't like that term too much, but streamline everything into a single schedule, a single environmental impact statement, and a single record of decision. Next slide. Next slide, please. All right, we have a slight delay. Oh, there we go. Thank you. So the one federal decision establishes a memorandum of understanding, and that's an agreement between all of the federal agencies that are involved on how to implement the executive order. There are a number of concurrence points identified within the process. And so there is the permitting timetable. This is prior to the publication of that notice of intent, working together to develop the purpose and need of the environmental impact analysis. The alternatives to be considered when drafting the environmental impact statement, identification of a preferred alternative, and establishing the concurrence process itself. In my next slide, I will now show you these concurrence points. There we go. So again, in the first timeline slide, I showed you the high-level overview of the leasing to operations process. This is kind of closing in on a smaller subsection of that process where we have the construction and operation plan submittal, and our agency conducts a completeness and sufficiency review. Now, this is one of the first points where we engage with all of the other federal agencies. And if it's not obvious, I haven't explicitly stated it, but this is an opportunity for the NOAA IUS to be involved with the, perhaps an opportunity for NOAA IUS to be involved with BOEM and the engagement and the decision making, and just to proactively participate in the process. So this is the first concurrence point, identification of the initial action notice, and then issuing the notice of intent. After that, there would be a public scoping process with all environmental reviews. There is a public scoping period, and then the drafting of the environmental impact statement. During the drafting of this statement, I mentioned before that this is where we identify alternatives to be considered. We would also perhaps identify mitigation measures to be considered, and they would all go into the draft EIS. Then the draft EIS is made available to the public for review. After the public review period, we would then issue a final environmental impact statement. After the issuance of a final environmental impact statement, another notice of availability would go out, and from there, we would have the one federal decision where a record of decision is issued to the public on how to proceed with a project. Now, during the environmental review process is where we'd identify mitigation measures. During the construction and operation plan, we have something that we call terms and conditions of COP approval, because the COP approval would also coincide with the issuance of the final environmental impact statement. Next slide, please. So how does the HF radar community, specifically on the federal side, find opportunities to contribute? They can be identified, you all can be identified perhaps regionally as a cooperating agency. You can contribute to the terms and conditions of construction and operations plan approval, or you all can help contribute, weigh in the development of mitigation measures for inclusion in the environmental impact statement. And again, because I'm not so certain of your familiarity with the environmental review process, a cooperating agency is any federal agency other than the lead, which would be BOEM, that has jurisdiction by law or expertise with respect to any environmental impact involved in a proposal or a reasonable alternative that would have significant effects on the quality of the human environment or environmental resources. Each branch of the renewable energy program, we all develop our own set of terms and conditions pertaining to a project approval. For example, we have our environmental review branch, the engineering and technical review branch, and we actually work closely with Coast Guard and incorporate some navigation safety terms and conditions of project approval also. And again, additionally, we all develop mitigation measures. So it appears to me that the HF radar community could possibly engage in both the environmental impacts, mitigation measures and terms and conditions of approval, as well as with the technical considerations for project approval. Next slide, please. And so in my last 2 minutes, I'm going to go ahead and briefly talk about the study funded by BOEM, radar interference analysis for renewable energy facilities on the Atlantic Outer Continental Shelf. This study was contracted to Booz Allen Hamilton, and it is complete and in the final stages of sign off for public posting on BOEM's website. Once available, it can be found under renewable energy studies, completed studies. Booz Allen Hamilton conducted computer modeling of radar systems potentially impacted in order to do line of sight and interference analysis. They conducted a discussion of mitigation techniques, and they performed a ducting analysis. The scope of this study considered 9 wind facilities. So radar interference impacts on the 9 total wind farms that were included in this study. Seven of them which were in planning stages at the time of this study kickoff, and 2 of them were based on hypothetical future scenarios that BOEM and Booz Allen developed together. The planned and hypothetical wind farms were in various planning stages and ranged along the U.S. Atlantic coast from Massachusetts to South Carolina, 5 of them being offshore the Rhode Island, Massachusetts area, 1 offshore New York, 1 offshore New Jersey, 1 offshore Delaware, and 1 offshore South Carolina. The radar types that were considered were airport surveillance radars, air route surveillance radars, NEXRAD radars, and of most importance to you all, CSON radars. Next slide, please. Here's a high-level list of the study conclusions and recommendations. Let's see, because I'm at the end of my time. Mitigation techniques available for offshore wind turbines are largely informed by research and lessons learned from onshore radar interference mitigation. Some operational mitigation options for CSON radars include data sharing from turbine operators and wind farm curtailment or curtailment agreements. Modification mitigation options include signal processing enhancements and antenna modifications. There may also be some relatively inexpensive mitigation options available for CSONs that involves a software upgrade. Mitigation techniques potentially involve wind farm developers and operators and the actions that they, as the developers operators, could or would require to take, including coordination in the planning stages of wind farm development. One thing BOEM is a big advocate of is encouraging developers to engage with the different federal agencies, not necessarily always going through BOEM in order to engage. Early engagement is important. Early engagement helps us solve problems, answers questions, all of those things. And so that's where we would point developers to the right points of contact within this HF radar operator community. It was also recommended as a result of this study that BOEM consider conducting line of sight analyses on nearby radar systems to determine whether major radar systems may be impacted by proposed wind farms. This study did actually do a line of sight analysis in the Vineyard Wind project. I'm sure many of you are familiar with that one. And so that's just a highlight of this study, because the line of sight analysis was not necessarily included in the draft environmental impact statement, but it is included in this study, which will be published soon. With that said, I'll stop here because I'm out of time, but you can go to the next slide, please. And you will find my contact information there. If you have questions for me, we're going into the question and answer period up next, but if you have very specific questions for me, or if you want more information about that study, once it becomes available, you can reach me via email or by my phone. Thank you.
Thank you so much, Angel. Another thank you to all of our panelists today. It's a tall order to get through 80 slides, more than 80 slides in a little bit more than an hour. So kudos to all of you for staying on time and for presenting so much material here. There's a lot for us to talk about. Brian, next slide, please. All right, so with that, we're moving into questions and answers. We have a lot of good questions from the audience and from the panel. I think maybe we'll start with a couple of sort of clarifying questions here. And a couple of questions about sort of the basic functions and kind of architecture of the HF radar network. Brian Zelenke, why don't we start with you here? When we were talking about beginning in your sort of overview of HF radar, the HF radar network, we talked about the notion that these can see well beyond what people think of as sort of the normal radar line of sight. What's the maximum range on these systems, and does it vary, or are they all say 150 kilometers? And so how do they vary, and what's the maximum range on these systems across the network?
So the maximum range is actually in excess of that 150 kilometers. It's in excess of 200 kilometers when conditions are favorable, and those conditions generally are the radio frequency environment, not wind or rain or wave conditions. The distance that they see out over the horizon does vary. It's always well beyond the horizon, but it can vary during daytime versus nighttime due to the radio frequency environment, and then also depending on the frequency of the system. I think my colleague Hugh already showed an image of that. I don't know if we can flip back through all that many slides, but that the typical resolution systems, long range versus a standard range versus high resolution, how far they look out. But yes, a lot of the systems are long range systems, and it is reasonable to have that 150 kilometer distance as being something you can expect day to day.
Great, thanks, Brian. And I guess another basic question about the network, can you clarify or remind us who owns and operates these systems?
So the systems are typically owned by the academic partner institutions that form the regional associations of the NOAA's Integrated Ocean Observing System. So NOAA does not, put it more simply, NOAA doesn't own the radars. It's the universities that operate them in partnership with NOAA that actually own them.
Got it. And those are operated then also by the partner institutions?
Yes. So the partner institutions operate these radars and telemeter their data back to NOAA, who integrates it into models. And NOAA also provides funding for this network and for the partner institutions. And that funding is provided through those regional associations, the logos of many of which you saw on that wheel diagram that I presented in my presentation.
Thanks, Brian. So thinking a little bit about the status of our understanding of the impacts and the issues associated with mitigation, I was on the EU Global Ocean Observing System website a little bit ago and noted that they have more than 100 of these HF radar systems in operation along their coast. And of course, they have now thousands of wind turbines deployed offshore, which begs the question, what's the status of this issue in Europe? What's been done to mitigate the problem there, and what can we learn from their experience? And I guess maybe I'm happy to just sort of toss that out to the panel if folks have knowledge of what's going on over there. So anyone, feel free to jump in.
I think Kodar Ocean Sensors, Chad and Deo, you guys have been involved with this more so than us US-based folks.
Sure, this is Chad. I'll jump in there a little bit. Well, yeah, I had mentioned that this issue was first observed over there in Liverpool Bay, and that first reference there was Dr. Lucy Wyatt at Sheffield University, and they had done some. That was the first, I think, so far the only network in Europe that has really observed that the impact on the radars. But the US, I would say, has a larger contiguous sort of and also longer range systems. I think our coasts are more completely covered. And so I know that they have done a little bit of work with mitigation over there. The system that was first impacted was a different kind of system. I mean, the same waveforms and whatnot, but it was a phased array style system. So some of the mitigation would be a little different there. But with the BOEM funding and the efforts that we've been involved in between Kodar and Rutgers, I would say we're farther down the path to having something operational. So again, it hasn't yet been as big an issue there, just I think due to the number of radars. 100 sounds a little high to me as being deployed and operating right now in Europe, but they have more wind farms, and so I think this is going to be an issue there as well.
Thanks, Chad. Dale or anyone else want to add to that?
Yeah, hi, this is Hugh at Rutgers. I guess one thing to note is, I think there's approximately maybe 50 to 60 radars operating in Europe right now, but none operate in the same vicinity of offshore wind. So they haven't been able to both simultaneously operate radars in field of view of wind turbines. So all the HF radar measurements that are taking place in Europe are done outside of wind turbine areas.
Got it. Thanks, Hugh. So thinking about mitigation, are there things that you all are looking at with respect to, say, sensor fusion? Could you, for example, deploy additional sensors within a wind farm, looking back towards the land, for example, to make up for lost coverage in the wind farm area, or network and other kinds of sensors that could help supplement the picture, if not directly in whatever the radar screen you're looking at and the models that you're using for various missions. I guess I'll throw that out to the panel.
Hi, this is Brian Zelenke. I'll take a first crack at it. And the answer is, in short, yes. I think it's important to remember what it is we're trying to measure here, which is waves and currents. So even though some of our downstream uses, like search and rescue, that the Coast Guard does could be informed by some sensors, it's certainly not like a sensor that is good for ship detection would necessarily ameliorate all of the issues that we would have interfering with a current and wave sensor, but it certainly would help. But more toward the point of integrating sensors within the wind turbine farms, I mean, if you think about it as a problem, if you flipped it on its head and said, well, we're going to be missing current measurements in an area, so what we want to do is we want to create a stable platform that has access to electricity and has data connectivity out in the ocean, so that we can put oceanographic sensors like current meters or conductivity, temperature, and depth sensors, or et cetera, et cetera, et cetera out there. The stunningly more expensive thing would be creating the platforms out there and getting the electricity and getting the data connectivity, and the minuscule cost in comparison would be the sensor that you would basically attach to the platform. Here we have an opportunity where that paradigm's entirely flipped on its head. We're already in the form of wind farms going to be doing all the really difficult, expensive work of putting steel in the water. It would be a tremendous missed opportunity if wind farms were instrumented in such a way that they could telemeter oceanographic data and meteorological data coincident with serving their mission of creating electricity. So I absolutely see the opportunity, not just looking backwards at land, but also looking forwards out at sea and within the wind field of the wind turbines themselves, using this as an opportunity to collect data. I think, as I showed on that graph at the beginning of my presentation, where you had basically two options for mitigation. You either have the right-hand side where I showed the spectra, and you can try to do something to help fix the sensors themselves, or you have the left-hand side where you can add additional sensors into the wind farm to collect similar data to those that the wind farm might deteriorate. I like the option C, all of the above, where we're going to be doing our level best to help come up with mitigations for the oceanographic sensors on the sensor level. But I think what will go a very long way to helping that is additionally having other instruments within the wind farms that can help provide similar data sets. And so with that, if others have thoughts on that, please feel free to chime in.
Others on the panel?
This is Dale Trockel. I just would like to kind of reiterate what Brian was saying, and the fact that his option C is definitely, in my opinion, the way to go. Just obviously you can help supplement some of that lost data with sensors on the wind turbines themselves. But if you remember back on the slide, it's not just the range cell that contains the wind turbine that gets impacted. And it's not just that small sector that contains the wind turbines that gets impacted either. It's spread throughout the entire range cell that contains it. So while you can fix some of the problem by putting in sensors, it's not going to solve the problem completely. And also with just doing the mitigation technique on the radars, I think you're not going to get as good of a mitigation technique without supplementing with sensors. So kind of doing some hybridization of that would probably be the best.
Hey, this is Anthony Krincich. If I could also chime in, I think that both Brian and Dale have talked about a really good way to do the hybridization. I just want to point out that in terms of a cost per unit effort or a cost per data point, there's still a significant cost to putting sensors on steel in the water, and someone has to maintain them, someone has to calibrate the sensors, someone has to go and do that. And so that should be something that the community thinks of if they're trying to find hybrid scenarios, to make sure that IUS as a system or our federal partners are able to get the observations that they need to move forward. And so I think that, you know, the radar systems provide a really significant value and are unique in a couple of ways that we talked about during these presentations. And I think having some observations in the field that would be part of these energy installations would be useful and super helpful. But I would point out that, you know, there are observations being made in the Gulf on oil platforms because there's a lot of oil platforms, but a lot of that data is simply not getting into the National Archive, being used with models and prediction systems in the same way that the radar systems data are.
Got it. That's a great point, Anthony. It's obviously you need to do more than just put sensors out there and figure out how to integrate those all effectively. Moving on, and it was Brian who introduced the mitigation white paper and the roadmap. How confident are you? And I guess this is a question for the whole community, that, you know, assuming we work through all of that, that we'll be able to make observations within behind large wind farms with the mitigation methods that are being investigated now, and how much, you know, will we be looking at degraded coverage still, or will that be back to normal, or what can we expect? And I guess that the input of Dale and Chad would also be very welcome there.
Yeah, this is Brian Emery. I think that's a really good question. And in my mind, it's an open question, particularly when you start talking about kind of hundreds or thousands of wind turbines, how effectively the radars are going to be able to measure the currents, not only within those developments, but beyond them. I think it's an open question. Maybe Dale has more kind of intuition or insight into how, you know, how much signal just a giant metal structure like that is going to absorb. One thing I should point out is the accuracy of the measurements are more or less a function of the signal to noise ratio. So if you have, so for example, in the Santa Barbara Channel, I have a radar with 4 or 5 oil platforms within the view. They're all about 4 or 5 miles away. And I've only recently been able to demonstrate that the currents that we get behind those platforms are not as accurate as they are at other sites. And so, you know, an oil platform is a much bigger structure than a wind turbine, but that certainly is an open question in my mind.
Great, thanks, Brian. Dale, do you have anything to add there?
Yeah, just as far as the shadowing impact, there's actually been a couple of studies. I don't remember the references right off my head. Chad probably does. But looking at that in particular about the shadowing effect of wind farms, and the initial results on that show that the shadowing for the wind farms at least is not really a very big impact for these systems. So as far as beyond the wind farm itself, just from looking at that, I would suspect that it's not going to be much of a problem. And as far as being able to mitigate it within the wind farm, I think, like Brian said, it still remains an open question, but I don't think it's ever going to bring it down completely within that. We might have some reduced coverage. And really, it comes down to our ability to estimate the rotation rates and nacelle angles. With that, we're able to recuperate most of the data if we were having a good way of either estimating that or getting those live streamed from the wind turbines themselves.
So that's actually a great segue, Dale, into talking about how you know, the HF radar community can work effectively with the wind industry and with other stakeholders to get the mitigations done. Can you just clarify on that point? You know, sounds like getting some kind of telemeter data about the rotation rate and the yaw angle of the wind turbines within wind farms would be really useful. Is that something that you expect that you would need directly from a wind farm, or is that something that you think you could sort of produce artificially, shall we say, based on observations of the wind and what you're seeing with the radar?
Yeah, so I mean, we can get estimates of it from with the radar and with cameras and things like that, but it's never going to be a substitute for having the real data set. So having a real data set allows us to calibrate our simulations to make sure we're getting the amplitudes of all of that interference correctly. It allows us to accurately test our ability to even estimate the rotation rate. So if we had a couple month-long data set, then we can see how well we can estimate those parameters from our cross spectra of the radar to see if it would be needed to have a live stream or not. But without that, it's really hard going forward without a verification, basically. And that's what the main use of that is, just to verify everything and calibrate.
Great. Go ahead.
Sorry, this is Chad. Yeah, I wanted to just sort of add on to what Dale was saying, and that is that, yeah, being able to, Dale's developing, the underlying models that can help us track and like, estimate what the turbines are doing, so that we can, determine where the interference is showing up or may be showing up that we can't easily detect it in the Doppler spectra. One of the things that sort of became clear to me was that, working with the Block Island turbines where there's only 5, is that, we in a single, range from the radar, we're looking at 5 different scatterers, and, their behavior, their operating characteristics can be totally consistent with each other, or they can vary amongst the 5. Well, now as I think it was Hugh or Brian, somebody said there's going to be hundreds of turbines in the field, and so if they were all operating sort of completely independently and inconsistently, this would be a pretty intractable problem. But knowing not just sort of what the radar rotations are and the nacelle directions and all that, to be able to help us with our onboard software, be able to detect and track these peaks through our data, but just knowing kind of operationally, what are the operating characteristics, what are the parameters within which that all these systems will be operating. And they generally operate fairly consistently because they're all sensing the same wind and trying to maximize energy extraction from the same wind field, although it will vary somewhat over the turbine field. But being able to know not just what they're doing when they're doing, but also kind of how we can better model that particular wind farm with the operational parameters involved would be very helpful.
Great, thanks. Maybe one more question on mitigation. We'll move quickly to kind of partnerships and collaborations, and then wrap up. So for Dr. Forbes, you mentioned that there's some potential for wind development to significantly affect the current and sort of wave environment, such that it might impact your modeling. What can the wind industry or what research do you think needs to be done to help sort of validate and or better understand those potential impacts and so that you can feed that into your models?
Yeah, I think there are several things. One is what you have been talking about, the mitigation of the original signals, and because that data gets into the Doppio model and the CPS model that are the ones we use for search and rescue. So that would be in the first phase. On the second phase would be models that take into account the wind farm. So we need the wind models that will accurately depict the wind deficit downwind, and we need the ocean models to accurately depict the current in the wind farm itself and around the wind farm, all the downwelling that I spoke about and upwelling, all those surface currents. So the best way would be to have a coupled atmospheric and ocean modeling system where the winds, the modified winds will drive the surface currents, and we could get a model that we can access through the environmental data server and have the correct winds and surface currents. So those are the main things I see that the scientific community could really help us and help with this problem. There are atmospheric models that already have some sort of high resolution parameterizations to be able to incorporate the wind farms, and so we basically need to get the correct currents, the correct models to be able to download them and do our drift modeling. And
got it.
So
thank you. So moving on real quick to partnerships and collaborations, maybe starting with Brian Zelenke. What's the best way for the wind industry to get involved in the effort to understand better and mitigate these impacts? Who should they work with, and what's the best way for them to tap in?
Well, certainly reaching out to myself and colleagues at BOEM is an excellent start. We would be the nexus through which you would be reaching the players in this, rather than going to specific academic institutions. So I think entering this at the federal level is good. I see a question here. Are any wind industry representatives involved in the community working group, and would you be interested in wind industry participation? I mean, speaking for IUCE, absolutely, I would be interested to see wind industry folks participating in our working groups and helping to address these problems and coming up with solutions. Because I really think we have an opportunity here if we play this right, where we're not looking at this as wind farms taking away our oceanographic intelligence opportunities. I see this, if we play our cards right, as an opportunity for wind farmers to greatly add to our oceanographic body of knowledge with the type of instrumentation that they're already putting in the water and then supplementing that. So I remain very hopeful that this is an opportunity for partnership and collaboration, and I absolutely invite that.
Great, thank you, Brian. And maybe we'll give the last word here to Angel McCoy. Building off of that, Angel, what's the best way for developers to work through with you how to address these issues in their construction and operations plans going forward?
Thank you. Really quickly, I'd like to mention that Brian Zelenke worked for BOEM up until a little over a month ago. So we actually have a really good working relationship with him and an excellent point of contact over there at NOAA IUCE. So wanted to mention that. But as far as developers go, we'd look for them to provide an assessment of potential interference along with possible mitigation options if necessary in the submission of their construction and operations plans. But in the end, BOEM, in coordination with other federal agencies, along with input from the public, we would, and even input from special interest groups or stakeholders, we would then develop the potential mitigations. Great,
thank you so much, Angel. And with that, I think let me give a big round of thanks again to all of the panelists today. I certainly learned a lot, and I think we've got a lot of good grist for follow-up. Again, just wanted to mention that we do have a follow-up conversation on R&D and potential collaborations. Please email one of the organizers of the webinar If you're interested in participating in that, I think we're still getting that on the calendar, but we'll send an invite around to whomever is interested on that, in addition to the steering committee that's been helping us put this together. And stay tuned for our next webinar on air traffic control and air surveillance radars in August. We'll be sending an invite out for that in the near future. With that, thank you again. Everyone, please stay safe and healthy out there, and we'll talk to you again soon. Thanks a lot.